Here it is. Okay, so welcome once again. So now we start with, let's say, some very basics, introduction and overview on s-SNOM. So I will start from the very fundamentals with some very simple schematics, but I also will show you some, let's say, in the end, with more sophisticated equations. So as said, it's a mixture of discussions with various people, what one should show in such an event and not. So I hope to get your feedback later on, whether it was too basic or too complicated. So let's start. This is a brief outline. So I will give some brief introduction to concept in instrumentation. Then we'll talk about the basic probing mechanism using metal tips. Then we will talk about background suppression using this famous higher harmonics demodulation. Then I want to talk about intensity versus interferometric detection. That's a very important point. Getting here maybe a bit complicated. And then in the end, the point dipole model, because the theory session later on given by Sasha is a little bit short, it's only half an hour, so I will talk a little bit about that. So, very brief history. Lucas gave a very nice history overview on AFM. There's also quite rich history on s-SNOM. Actually started with Sinch 1928, but I really don't have time to talk about that. So I started in the mid of 90s, where this basic idea was developed, namely by Wickramasinghe at IBM, 1990. They made a patent on using a standard atomic force microscope tip, shining light on the tip, and then collecting the backscattered light while recording the topography image. And that should give nanoscale resolution. As said, they had a patent in the 90s, and then this famous science paper in 1995, where they show this image, where they claim 7 angstrom optical resolution in the visible. Should say this hasn't been reproduced so far. I think nobody has reproduced it. Nevertheless, it's a famous paper, and it was, one could say, the starting point. And then other people like Kawata, Bachelot, and particularly Fritz brought that idea then to the infrared spectral range, and that's here this famous paper from Fritz from '99. That was just in the year where I started, or 1 year after I started to work with Fritz, where they showed infrared spectroscopic contrast on the nanometer scale, and one could say that was really the kind of beginning of all these developments that then led later on to NeoSpec. This was what 98 was the time when I started. So again, we scan the surface, we collect the light scattered by an AFM tip, and we get nanoscale images. Sounds easy, but there's a lot of details behind, and I want to talk about that. Before we start, you probably all know the setup. I think I saw it from the motivation letters and a little bit the introduction that you gave about yourselves. Most people are here have a s-SNOM from NeoSpec, and I use this. Nevertheless, I want to briefly outline here how it works. So the AFM is a standard tapping mode atomic force microscope microscope. We use typically standard AFM tips. They're typically coated with a metal. You can see here an SEM image, here a light microscope image, actually seen through the parabolic mirror of the s-SNOM that we use for focusing a laser beam or a synchrotron in some cases onto this tip apex here. So the tip is fixed, it's oscillating at the resonance frequency, the fundamental resonance we use that Lucas explained. They call it omega, and we scan the sample. This is important because we want to keep the tip all the time in focus while scanning. So the sample is scanned, this is important. Then we use a parabolic mirror, as Fritz pointed out. That way we can focus any type of light. So from, let's say, visible, 500 nanometers, no problem for aluminium. And we can do this down to 1 terahertz, even less. In the Fritz lab, he used once, I think, 300 gigahertz, and still with the same parabolic mirror, this works. So that's a focusing element. So if you do imaging, then we use monochromatic lasers. That's typically a CO2 laser or quantum cascade laser or frequency tunable OPOs, and we illuminate the tip. Then we use typically the parabolic mirror and collect the backscattered light and direct it to a detector. And now there are 2 important things about which I will talk in detail. So the detection is done twofold. First of all, we use a Michelson interferometer. This has many important reasons. First of all, for full background suppression. And the other thing is we can get amplitude and phase images or spectra to map the dielectric constant, which is complex valued. So this is important, 2 important things. And another thing is that this interferometrically detected light on the detector, we detect by recording at a higher harmonic That means not at the frequency of the modulation, but at n times the modulation frequency. And that's important to suppress background scattering. So I will talk about all that in detail. So just if we use monochromatic imaging and we use this interferometer, then we do this typically with a so-called pseudo-heterodyne interferometer, and that's the technique that is probably the most flexible at this moment, because it can be used with any type of wavelengths, and we have one talk dedicated by this, given by Martin Schnell, so I don't want to touch that. So he will talk about fundamentals, but also about practical details and problems that one may face with this technique. So then the same setup in principle can be used not only to perform imaging, but also to perform spectroscopy. And in this case, we replace the monochromatic laser by a broadband laser source, for example, a difference frequency generated wave by broadband laser. That's also what you can buy with the s-SNOM. But one could also use synchrotrons, and actually is then the talk by Raoul Freitag, who is sitting here already. He will talk about nano-FTIR, and he's doing that with synchrotron, but we can do it with even with a glow bar if you have enough patience. And okay, so now this Michelson interferometer is used as a Fourier transform spectrometer, and again, I don't want to go into detail. It works similar to a standard FTIR spectrometer, but it has a couple of important differences. It's, for example, an asymmetric Fourier transform spectrometer, and for that reason, one gets amplitude and phase spectra, which is what you do not get in a standard FTIR spectrometer. That's very important because from amplitude and phase, you can learn a lot of interesting things that you would not learn if you just measure intensity. And there will be multiple talks about that, so I don't go into detail. So just again, refer to Raoul's talk. So I want to come now about the basic near-field probing mechanism, and in most cases, we use metal tips. That is maybe not the case if we do polariton imaging, but in most cases for dielectric mapping, material contrast mapping, use metal tips. And let me start with a tip, isolated tip, here schematics, and that's a numerical simulation in the absence of any sample. And as Fritz mentioned, this tip here acts as an antenna, and there are different ways how one can describe this antenna. It depends on in which spectral range we are, how long it is. So that simulation shows a terahertz wave of 118 micrometer wavelengths hitting a 1 micrometer long tip. So here we're in the terahertz, we don't have plasmonic resonances. We have 1 micrometer tip, which is much shorter than the wavelengths. So we have neither an antenna resonance nor a plasmonic resonance. What we have here is a classical lightning rod effect, or what is called a lightning rod effect. So what happens is that this field here, typically it's p-polarized, such that the electric field points along the axis here. It polarizes the tip. And if you take a snapshot in one moment and we look at the charge distribution, we see charges in the tip apex and the opposite charges here on the base. And in the tip apex, these charges are squeezed together, and that gives rise to an enormous field concentration in an electrostatic picture. Now, of course, this is oscillating at terahertz frequencies or infrared frequencies, so it's just, as I said, a snapshot picture. But in this electrostatic picture, you see this enormous accumulation of charges, and that gives rise to strong field concentration, which you can see here in this red color here. And that depends essentially on the tip radius and is independent of the wavelength. Doesn't matter whether you use visible light or gigahertz, you will get here focusing of the incident radiation on the scale of the tip radius. In principle, you can go down here to 1 atom, and you could, through an atomic lightning rod effect, you could focus light down to atomic scale dimensions. And this is done not with the s-SNOM, but with the SDM-based techniques and fluorescence, PL, and so on. This is not the topic here. Okay, so that's the simulation. So this shows that it works. We get here 20 times field enhancement. That means 400 times field intensity enhancement, which is quite a lot. So in this schematics, we can depict that. This polarization gives us a dipole, here this red arrow. And now light comes in, it induces the dipole. We create this near field here, schematically drawn. This near field is just hanging around here. It's not really doing anything. Yeah? It's just there. And then this dipole scatters, right? So that's what happens. So this near field, you wouldn't normally notice. But now we bring the sample close, and then if you are here a certain distance away, nothing happens. The near field does not reach the sample. But once this near field, to a certain extent on the scale of the tip radius, once these near fields reach here the sample surface, then these near fields, similar to a propagating wave, they can be reflected. A very simple picture. And this reflection can be actually described by Fresnel reflection coefficients. And in the electrostatic limit, this reflection coefficient that we typically call beta has a very simple form here. It's epsilon minus 1 divided by epsilon plus 1. And epsilon is the dielectric function of the sample surface here, which is a complex number. Now, the back reflection of this near field to the tip induces a kind of an additional polarization in the tip. And I draw this here by a blue small arrow. I use the blue color not because there's a frequency change. So this is an elastic process, so elastic light scattering. Blue, this only means it's near field induced, right? But otherwise, the frequency is the same. We always stay in the whole course in the elastic regime. Now, this tiny little dipole, it scatters this blue light here. And now, if you come closer, of course, more near field is reflected, and the additional polarization intensifies, and we get more scattering. So that's why I draw this blue arrow a little bit more intense. So now, actually, we are not interested in the red arrow, because this red arrow here just tells us nothing about the sample. It's just scattering from the tip. So we want to detect this blue arrow here, right? And the red one here we can consider as background scattering, actually. And so that's now the trick that we need, or the tricky thing that we have to solve. So how can we measure the light that is scattered through the near-field interaction? So what we call the near-field scattered radiation or light, okay? So here you can see this again in the numerical simulation. Now the tip far away from the sample and now in proximity to the sample, and we can see indeed that this near field here intensifies. That gives rise into this additional scattering here. All right, so that's a very basic physics. But now, as I said, we want to detect here this blue light here, and we want to get rid of the red one here. And there's a standard technique, is this so-called higher harmonic signal demodulation. And to understand that, I make here a couple of very simple schematics. And it goes as follows. So what I plot here is this, the light that is scattered from the blue arrow, so the near-field induced scattering, ENF, and I plot this as a function of the tip sample distance here, Z, right? This is schematically drawn, not really calculated. And what we see is that if you retract the tip here, then this near-field scattered light, it drops down on a scale of the tip radius. And if we are then further away than one tip radius, there's no near-field signal, simply because the near-fields do not hit anymore the sample surface, okay? So this happens on a scale of the tip radius, typically 20 nanometer, and it has a strongly nonlinear dependency with distance. Now, on the other hand, we have the light that is scattered from here, the direct illumination of the tip, so the red light, so to say. Now, what I didn't say yet, if you are close to a sample, so the tip is illuminated directly, but it also illuminated indirectly via reflection at the sample surface. And then the scattering goes directly and indirectly via reflection at the sample surface. This is something that very often is forgotten, but it plays an enormous role, and we see then a couple of talks later on where this effect can be very disturbing, and Fritz actually mentioned it slightly, and which we can get rid of by taking ratios of harmonics. Now, that's a calculation, an analytical calculation, actually. What happens if a light beam, here Gaussian beam, is reflected at the sample surface, and then the tip is just drawn in there. It's not taken into account in the calculation. What happens is that the standing wave pattern builds up, right? We have maximum and minima of field intensity because the incident beam and the reflected beam, they interfere. You see the standing wave pattern here, right? Now, if you move the tip up here, then the tip apex here is exposed to either maxima or minima. And then the light that is scattered here from this red arrow, it modulates. It oscillates here, which reflects the scattering due to this standing wave pattern here. And that happens on a scale of the wavelengths, because that's a far-field interference effect, and we all know far-field interference effects cannot lead to structures in the light that are smaller than half the wavelengths, or the wavelengths roughly, right, in this range. So now we have these two very different length scales here, and now we make use of them. What we do now is we bring the tip very close, and we look here in this tiny little area. You see, if you now start to move the tip, which we're anyway doing because we operate in tapping mode, If we move the tip here up and down, we see that the tip will go through a field that is strongly nonlinear with distance. While here, well, this is pretty much linear, right? And now this is schematically drawn. Let's see what happens if we have the tip far away, and then we bring it closer. So the green spot here marks the tip position, and I have here now. Here I plot the tip motion, and we make this now sinusoidally. So we start far away, and then we have no near field, but we have a little bit of background signal, right? So then we move slowly towards, right? So you see that the tip now samples this nonlinear near field signal, but this more or less linear background signal here, right? And the tip motion is kind of sinusoidal. So we have here a sinusoidal motion. And this sinusoidal motion then leads to a signal due to the near field and due to the background signal. So, and that's key here. So what we see now here is that this tip motion is sinusoidal per definition because we drive it via an electrical signal that is sinusoidal. Now the background, because this behaves more or less linear, the detector signal will be sinusoidal too. So it will be harmonic in time. Whereas the near-field signal, because of this nonlinearity, we see that this signal is not harmonic anymore. It's not a nice sign. It's kind of a distorted sign, right? So it has here, the base is a little bit broader, and this is a sharp spike here. Now, what does it mean? This means simply that if we now Fourier transform each of these curves here, we get the following. So now, the tip motion by itself, the tip motion is a sine. If you Fourier transform a sine, we get one peak in the Fourier transform, namely exactly at the modulation frequency omega here, right? Now, if we can do the same for the background, and the background has an offset, right? It's not going down to 0. For that reason, we get a Fourier component here at DC, at 0 frequency. Then, of course, we have the modulation frequency, and because this is not perfectly linear, we get here some slight deviations, and we may see a second harmonic because of a slight unharmonicity. That's important, because I want to point out, second harmonic demodulation is not always background-free, and the reason is that this background here does not behave exactly linearly as a function of distance. Now we look to, this is more important now, through this strong nonlinearity, the strong deviation of a sinusoidal motion gives us the generation of a lot of higher signal harmonics. So these are not light harmonics, right? This is not higher harmonic generation like you do in a nonlinear optical process. These are signal harmonics. This is because I oscillate the tip in tapping mode at omega, and then the detector sees a DC signal, then at the modulation frequency a signal, but at different harmonics. And they can reach up to the 6th, 5th, 4th harmonic, we get a signal, right? Because of this nonlinearity. And this is absent here. So the only thing what we need to do is we look at, let's say, the 4th harmonic, and we get a signal that is only through this near field. But here there is no 3rd or 4th harmonic signal that arises due to the background. So, and that's the trick here. So if we use a log-in amplifier and we switch it to 4 times the oscillation frequency of the cantilever, we will get a signal which only reflects the near-field signal, but not the background. So to demonstrate this is the case. So this is some old measurements that I actually did back when I did my PhD thesis with Fritz, and this was done in the visible. And here one can see very nicely these background oscillations. So what we are doing here is a so-called approach curve, or one could also call it retraction curve, depending how you see it. So what happens is we have the tip that is oscillating at omega, right? So it's illustrated here. The oscillation amplitude is delta z. And then we have the tip at a certain distance. And this distance, called z, is the distance between the lower turning point of the tip oscillation to the sample surface, okay? So 0 means that we're in contact. Now this 600 means that here, that's 600, that means that's the lower turning point, okay? And now we don't change the amplitude of this tip oscillation, we just bring this closer, or we retract, approach or retraction curve. And now we shine light on the tip and we collect the backscattered light. And now the first thing we do is we look at the signal, the detector signal, demodulated at exactly the modulation frequency, and then we get this here. So we see the signal drops, but then once we are far away, many tip radii, many 100 nanometer away, we see these oscillations, right? And these were these oscillations that I schematically have drawn before here. these oscillations, more or less, that we see here, right? So we don't, it's hard to see the near field here. There's a near field, but it's hard to see. So how can we suppress it? Now, we just take the log-in amplifier and we look at 2 times the modulation frequency, and what we see is that close to the sample surface, there is a strong decay in the near field signal, and then we see a couple of oscillations. Now we go to the third harmonic, and we see there's a signal. It drops really dramatically, really quickly, within 10, 20, 30 nanometer, and then it's gone, and then we have only noise. And that's the pure near-field signal. That's the pure near-field signal. Here, a little bit of background, and here we have a lot of background. And so that's the trick. Here now we have an image in which one can also see that visually. So here, that's a test sample. These are gold islands on silicon. And you may all know already, and we will come to that later, that gold appears typically brighter in a near-field image because it has a higher refractive index than silicon. And near-fields are reflected stronger on gold than on silicon. So now if you would look at the signal demodulated at the oscillation frequency, we see, first of all, a lot of strange interference phenomena. They shouldn't be there because the sample has not such features. And on top of that, the gold triangles are dark. They shouldn't be dark because they reflect near fields better, so they are dark. And the reason is that that's a so-called topography artifact. It's not real. It's somehow a sharp optical contrast, but it's kind of useless. It does not give you information about the local refractive index because of these background oscillations here. Now, if you look at the third harmonic, where we don't have this background in this approach curve here, we see beautifully a very clean image, no background interferences, and we see that all the gold islands are brighter as the silicon because the refractive index is higher, which we will see later on why this is the case. And I want to point out, and this is what I see very often, people are not doing this anymore. 10, 20 years ago, these approach curves were a key feature if you did an experiment in the lab. You always check, first of all, is my measurement really background free? And the only way of finding out that is you look at all the different harmonics, and then you check that the signal drops, and then over a long distance, it's gone, there's only noise. And then you're sure you're background free. And then you can trust this image. If you just see this image, well, it's hard to say. So that's my recommendation always. Look at approach curves or retraction curves, however you want to call them. Now, this was in a visible, so we repeated this experiment just for this workshop to see a nice comparison between visible. That's actually what Adrian requested. So a comparison between visible light at 540 nanometer, and now here in the mid-infrared spectral range. And you see already there's a dramatic difference. These oscillations vanish, and the reason is that the standing wave pattern in infrared, of course, is on a much smaller scale because this fringe spacing is larger, right? So the fringes, they would do like this here, right? Because the wavelength is nearly 10 times larger here. So if we make an approach curve, we zoom out here, then we see that these oscillations are still there, right? But what we see is that the background suppression altogether is better in the infrared spectral range, simply because these long-range oscillations due to this background interference, it gives less background signal, right? Because the variations are more linear as a function of distance. Nevertheless, if you look at the second harmonic, and this was done, I think, on silicon or gold, at a standard tapping amplitude, the second harmonic is not background free necessarily. So be careful. Using the second harmonic is tricky. Check carefully whether you can do that. With biological sample, very often you don't get a third harmonic, and then you have this tiny little background here left. But watch out the next talk by Martin. He will tell you a method how you can correct for that if you have amplitude and phase images. Okay, so that's more or less what I wanted to say. Then what is also interesting to see is that this decay here becomes steeper and steeper, and I will have further slides on that. This kind of faster decay of the near-field signal one can use actually to increase the spatial resolution, and that is what I think Fritz invented that word. He called that virtual tip sharpening. You remember that? Many years back? I don't remember whether it was here. So, and if you measure at a higher harmonic, because of this faster decay of the near-field signal, you get a better spatial resolution, okay? But again, try to make large approach curves if you go to the infrared spectral range, because it's hard to say whether this is background or not, but here you see it very clearly, okay? Okay, so far we talked about fields. Okay, I didn't talk about any detector signal. What I was analyzing so far, at least in the schematics, were fields. What I showed you here were detector signals. But now we need to see a little bit what are we measuring actually. And I start here from a very, very basics because I said I discussed with various people and they recommended me to start from the very basics, talking about amplitude and phase. Because in optics or in optical spectroscopy and imaging, measuring phases are not necessarily what people do. So typically intensity is recorded. So that's why I started from the basics. So we come in with a wave, and we describe this wave here. That's a typical equation for a wave. We have a cosine, kx minus omega t. K is the wave vector, x is the spatial coordinate, omega is the angular frequency, and t is the time. Okay, so that's the time oscillating part, and that's the part that oscillates in space of this wave. And I just put a 1 there just for normalization. It's not really important. Now, let's look at the scattered wave. The scattered wave now, two things can happen. First of all, this wave has an amplitude, right? And this amplitude we denote in the following S for scattering coefficient in amplitude. But it could also happen that the phase is shifted. And this is typically not measured in an intensity measurement. But this phase shift is essential in s-SNOM, because as you will see later on, this phase shift encodes absorption in the sample. Also, this is a scattering experiment. So by measuring this tiny little phase shift, we can measure the absorption in the sample, which in an intensity detection would be lost. And that's one of the reasons why we measure interferometrically. So this we describe then, the scattered field now is S multiplied by cosine. Then we have the same expression again, plus this phase. I want to point out, we call this phi very often phase. And I mentioned it recently to a couple of people, and they said, no, this is not the phase. That all is the phase. And this is true, actually. All of that is the phase. This is the phase shift. That may sound picky, but depending with whom you talk about, it may make a difference. So what we measure is the phase shift, okay, and not the phase of the wave. Because only the phase shift is meaningful. The phase can be random. It depends on how you define this phase here. So now, what you see in future lectures or what you see in literature, and adapting here to literature, typically we don't write, this is all written up in real numbers, but if you deal with amplitude and phase, it's more convenient to write all the mass in complex numbers, and then we describe this with a complex exponential function, where now this transforms into this. The incident field is e to the power of I chi x minus omega t. And the scattered wave, then we do the same exercise here. And after a little bit of algebra, we come up with this. The scattered field is proportional to the incident field. And then we have here this complex number here, which has an amplitude s and a phase shift phi. And this we can summarize, or we typically summarize to sigma. And the sigma is a complex number. It has an amplitude, it has a phase, and that is what we call the scattering coefficient. And I don't distinguish here between background and near field. It's just the scattering coefficient for this moment, okay? And if you think of the microscope, what it gives you in the end, the OA and the OP signals, right, in the s-SNOM, for example, they would correspond to this S and to this phi here. So, and then we define, that's the scattering coefficient. In the end, it is complex number. It's the scattered field divided by the incident field, all right? And again, I said this already, amplitude, this is the phase shift in reality, but it's very often the phase. And now that's also a very useful thing, and we will see this later on in some presentations. We can describe these scattering coefficients, or we can visualize them in the complex plane. We have here the real part, here the imaginary part. So a 1 would be just along the real part. The length is 1, and the angle is 0. And now the scattering coefficient corresponding to this wave is changed in amplitude. It's a little bit smaller. That means the length of this vector is shorter. And then we have a phase shift, and this phase shift goes in this direction. That's another important thing. So actually the sign of the phase, that leads to a lot of trouble, as we will see later on. So, and we define actually in s-SNOM, if you have an absorption or something like this, then the phase shift is positive. But we will come back to this later on. You will also be able to see negative phase shifts, which can be very confusing, and there will be a separate talk on that. All right, so now that's the scattered wave. And now we come back to that we have to distinguish between a near-field scattered field, ENF, and the background scattered field, EBG, I call it, okay? And now we can, so far, I just say I have one sigma here, one scattering coefficient for the totally scattered light. Now I can introduce a scattering coefficient, a complex valued one, for the near field and for the background, okay? And then I have the near field scattered field plus the background scattered field, and then I have the sum of the two coefficients here, and so on. Now each of these ones is a complex number. And now I have an SNF and a phi NF. This we call the near field amplitude. This we call the near field phase. And we can do the same exercise for the background. So we have a background amplitude and a background phase. And in a complex diagram, this would correspond to two arrows here. Each have a different length and each have a different angle here, okay? So this is what happens if we are in the domain of fields, right? This is fields, but no detector measures a field. Detector measures intensities. And the intensity of the scattered field is proportional to the absolute value of the scattered field squared. So that's a pretty nonlinear process that the detector is doing there, right? So the field is squared. And that gives a lot of trouble, actually, as you can see as follows. Now, the tip is not oscillating now in this moment, okay? It's just static. So now, let's put this expression here that I put here for the scattered field. So then we can, U stands for just the detector output, like the detector voltage, right? So now if we execute this square here, which we can do by taking the scattering coefficient for the near field plus the background, and then we multiply it with the complex conjugate. That's in principle what this absolute value squared means. Now, if you do this exercise, and it's very simple school algebra in principle, we will see the following. And this reminds a little bit to what the interference equation that Fritz showed already before. So the detector signal now is the following. The near field amplitude squared plus the background amplitude squared, that would correspond to the near field intensity, the background intensity. And then we have here this interference term in which the background amplitude, the near field amplitude, and the near field phase and the background phase are completely mixed up, all right? So this term is a mixture of a background and a near field. This is the background intensity, and in principle, if the tip is statically above the surface, this is so large that you will not see anything else because the tip is so massive and is scattering so much that this is always the dominating term. So you will only see background if you just measure this. This is a tiny little bit, and this is a complicated interference term. And there you can see already that if I just I have no chance getting here, in principle, I want to get the blue numbers in this equation. I want to separate these blue numbers here, right? So how do I do that? And that's tricky. And I showed you before already that we can separate on the level of electric fields. We can do this demodulation technique, right? We now start to move the tip up and down. And then we modulate the near field signal and the background signal. So I showed this before. These are these Fourier transforms for the fields, right? So the scattered field, I can write as a Fourier series, now expressed as Fourier coefficients for the near field, NF. N is the harmonic, right? So that's just a mathematical series if I sum all these Fourier coefficients up here, okay? And I can do the same for the near field. Now, that's the scattered field. Once I start oscillating here, through the nonlinear tip-sample interaction, I get this series plus this series. Okay, that's the scattered field. Now, I can summarize this. At each harmonic, I can sum up the complex valued scattering coefficients. So this is due to nonlinear tip-sample near-field interaction. But now, we have a second nonlinearity, namely this square here. And now we have this from minus infinity to plus infinity complex valued sum, and we have to square it up. So if you write that out, you can write an equation, and it will never stop, okay? So this is really a complicated equation in which we have now mixed up through the squaring all type of near-field amplitudes and background amplitudes at the various harmonics. So I don't execute this, and the next step that is now, it's really fast. I mean, you can do this exercise eventually by yourself. But so what we are doing now is the following. as I said, this is the detector signal written up on the basis of this scattering model. But now I can just say very generally, okay, the detector signal is a complicated signal, and I can describe it as a Fourier series where I have un. This is the detector signal at the nth harmonics, right, of the modulation frequency. And now I can make a kind of a coefficient comparison. And then I see the following here. I can see that the demodulated detector signal has now this form here under certain assumptions that I make, right? I assume now that at higher harmonics, we have essentially near-field components, but no background components, right? That's the important assumption. And if we plug this in and then we make this comparison, as I said, this is really lengthy mathematics and algebra, you have to believe me, then this comes out. So the detector signal at an nth harmonic is, again, this rather complicated interference term here, where we have the background signal at DC, the unmodulated background signal amplitude multiplied with the nth harmonic near-field amplitude, and then we have here the phases, the phase difference between the near-field phase at the nth harmonic minus that one at DC, all right? So that means also I now make modulation and demodulation, and also I showed you before that that solves the problem. Obviously, it does not solve the problem because now I mix up here near-field and background signals, and in principle, one can understand this scattering process as follows. There's an interference between these two terms, right? There's a background field, and this background field interferes with this near-field signal. And so you will be never actually in such an experiment be able to measure a pure near-field signal because there's always this background, and this background acts as a local oscillator or as a kind of a reference field. And we will see in the next slide how we can solve this problem with a real reference field. The problem with this background is we don't know anything about it, and we have it barely under control because it depends on how we align the setup and so on, okay? So that's a little bit the problem. So this does not work. So don't just close your interferometer and measure. You take an approach curve, you will see that actually all the harmonics, at higher harmonics, the signal will go down to 0. And you may think, oh, I have a background-free signal. But if you do that without an interferometer, you will see this here. Because you can see it here. Once the nth harmonic of the near-field signal is 0, as this is all multiplicative here, the whole signal will go to 0. Also, you have the background here multiplicatively in. Okay. So now we come to the topic of interferometric s-SNOM. Now, so far, in principle, we had here the laser, we focus it on the tip, and we go backward like this, right? That was what I described so far. Now, what we are doing is we put a beam splitter here in the path, such that one beam goes straight through on the reference mirror of the Michelson interferometer. And that is what you have in the s-SNOM. And now what happens is that the detector now sees the sum of the background and the near-field signal, but it also will see what we call the reference electric field, right? And it ends up here. And that's a classical interference phenomena. And I don't talk much about it because that will be in the talk after lunch. We will hear much more about that. So I would just show this a little bit, coming back to the equations that I had before. So remember, on the slide before, I had these two equations. So the scattered field, expressed in scattering coefficients. Because of the tip oscillation, we get this complicated sum. But now we add here to the detector not only these demodulated background and near-field signals, but we come here with this reference beam. Okay? And so that means simply that we have this sum here, but we add here this green number. To the slide before, the only novel thing that I'm doing here is I make here plus electric field of the reference beam. And now the important thing is the reference beam, we know, because the reference beam we can control, right? The reference beam is reflected at a reference mirror, so we know very well its intensity, or we can control it. And the reference phase we also can control. This is very different to the background field, about which we don't know anything. So the reference field is independent of the alignment of the parabolic mirror. Right? And that's why it's a well-known reference field, while the background is something that is, well, diffuse, spurious, dangerous. Then we can do the same here, right? we write this sum up. Now it's getting even more complicated. I don't go through the math, but we now can make, again, a coefficient comparison. And we make the similar assumption than before. And then we see that the demodulated detector signal now is this term here. That's exactly the same as in the non-interferometric case. Remember this? So this was non-interferometric detection. So we have this term again. But now we have this additional term here, which is very similar to this one. But instead of the unmodulated background amplitude and the unmodulated background phase, we now have the reference amplitude and the reference phase. And as I said, these are two numbers or two quantities that we have fully under control, and we know them. All right? So now still, we have the problem. Now, we are interested in the blue numbers. We want to extract out of this equation the blue numbers. So how we are doing this? Well, we try to get rid of this term here. And how can we do that? We can do that by making the reference beam much stronger than the background field. And in some cases it works, but in a real experiment with an s-SNOM, it doesn't often not work because you would blow up the detector or get it into saturation. So this is a little bit of a tricky issue. You cannot do that necessarily. We can do that with pseudo-heterodyne detection, and Martin will show you how we can do that, but I leave it then for him. So now, for the moment, let's assume we eliminate this term too, then we have this one left. But now we still have not the blue numbers, we have these, well, the green numbers, let's assume we know them, right? But then we have the amplitude and the phase mixed up, so we need to separate that, all right? So again, this here, I said we can set just by definition, we set it to 1, and then we have the detector signal is the amplitude multiplied with the cosine of the phase at the nth harmonic, and only the near field is there. So now, how can we solve the problem? And actually, in the very first experiments that I did in the infrared with Fritz, we did the following experiment. It was not very sophisticated. It was the most simple quadrature-homodine experiment that you can think of, and it's not very practical because it's slow. But it's very simple to understand what we are doing here. So we have the reference beam, and we just move this mirror by a distance of lambda over 4. Okay. That means that the reference beam in the one situation travels 2 times lambda over 4, right? That means lambda half. And then what we can do is simply, then now we have at mirror position A, mirror position B, and then we measure the detector signal. And once this detector signal is the amplitude multiplied with the cosine of the phase, and then because of the phase shift of pi, well, pi over 2, sorry, we get here amplitude multiplied with a sine. And then we just take we sum up the squares of the detector signal and take the square root, and we have the amplitude. Or we take the ratio of the two detector signals, take the arctus tangents, and we get the phi. And now we have nicely amplitude and the phase resolved. But careful, this only works in case that the reference beam is strong, which, as I said, typically is not the case. And the solution will be presented by Martin Schnell then. Okay, interferometric detection then has many more advantages. I don't want to talk about this because time is running. So next thing I wanted to talk a little bit about is the dipole model. And so now a model. How can we understand it? So far everything was a little bit pictorial, and I want to illustrate now this dipole model that actually also comes from Fritz's lab, from Bernhard Knoll. Actually, he started to develop the first of these models. And let's start with the numerical simulation again. So here you can see a tip and a small sphere under different polarizations. Here we have a polarization perpendicular to the tip, and here along the tip here. And what we see here is that the field distribution at the very tip apex here is pretty similar to the field distribution of a small sphere here. So if you just look below this line here, right? So if you are just interested in modeling the field distribution below the tip apex, we can actually replace the tip with a sphere. That works somehow. It works qualitatively very nicely, but quantitatively not. But qualitatively, with this kind of sphere model, or sphere replacing a tip, one can describe nearly every experiment in s-SNOM, at least that I'm aware of qualitatively. Okay? That's why I think it's very powerful. You may not want to do that for making accurate quantitative modeling, but if you have a phenomena that you don't understand, then this model is very simple to implement, and it's very intuitive and simple to understand. So what do we do in this model? Well, we replace, as I said, the tip by a sphere, and the sphere, an isolated sphere, in the electrostatic limit, and if we have a 10 micrometer wavelength and we shine it on a sphere that is 20 nanometer, such that it fits into the tip apex, then we are in the quasi-electrostatic limit. Retardation does not play a role. And then in this electrostatic or quasi-electrostatic limit, the field distribution around a sphere is exactly described by that of a point dipole that sits exactly in the center here, right? So, and this point dipole here has this analytic, very simple expression. That's the dipole moment here. We have this expression here, a to the power of 3. A is the radius, so that's kind of the volume. And then we have here this factor epsilon t. Epsilon is now the dielectric function of the tip material. Epsilon minus 1 divided by epsilon t plus 2. Right? So that's the so-called polarizability of the sphere. So in the end, the dipole moment is the vacuum permittivity multiplied with the polarizability of the sphere multiplied with the incident field. So that's very simple. And that can be quickly and analytically modeled. Now, I want to have a closer look. And now, actually, in the whole, I noticed after we had every lectures together, nobody really talks about what's a near field, actually, and what's the difference between a near field and a far field. And I was thinking, OK, so a near field is something that, by definition, does not propagate, right? It sticks to the tip. But in the end, the detector is in the far field. So how does the near field get to the detector? Because, in principle, the near field is a non-propagating wave, but somehow it propagates to the detector. And that's why I made these slides here, where we see that's an analytical simulation, so based on this simple equation here. So the equations that these are here simplified versions of the standard Hertzian dipole. If you go to Jackson, for example, electrodynamics, you find this long expression for the Hertzian dipole. And now if we are in the near field limit, that means we are here in the near field limit, that means the radius is much smaller than the wavelengths, and we look only nearby, then the near field is given by this equation here. That's the classic electrostatic dipole moment. P is the dipole in a vectorial writing here, and R is the distance, so how far we go away. So that's an electrostatic field, but we're doing optics, and for that reason, we have this term here, and that's an exponential function where we have minus I omega t. So that's a harmonic time dependency. So that means this electrostatic dipole is oscillating, right? So the signal is changing in time. But that's not a propagating field, that's an oscillating field. If we take this Hertzian dipole equation and we look then far away, so look, the scale here is different, right? We are now on the scale here on a sub-lambda scale, and here on a scale that is much larger than lambda. And what we calculate here are now in the far field limit. That means the radius where we execute the fields are larger than lambda. And this black circle here, that's not the particle. It's just blacked out because we would have a divergence here because the electrostatic field is diverging at 0, right? So that's now the far field. That's the near field, that's the far field. And we see already that the two fields are rotated against each other by 90 degrees. So the near fields are oriented along here, the pole of the dipole, and these guys here are perpendicular. So while the near field is maximum here, in longitudinal direction to the dipole, the scattering goes perpendicular to the dipole. But this is just basic physics. So now we need to put the detector here, but the object we need to put here, right? And now if we look at this equation, this Hertzian dipole equation, then we see that the scattered field, as well as the near field, is proportional to P, the dipole moment. And then it decays with 1 over r, while this decays with 1 over r to the power of 3. And then we have this exponential term here, but now look, there's a tiny little difference. Here we have omega t, here we have omega t, but additionally here we have the k wave vector multiplied by r. And that describes a propagating wave. So the field is oscillating in space and in time, while here it's only oscillating in time. So that's an evanescent non-propagating field, and that's a propagating field, right? Now, but what we see now is that both the near field and the far field depend on P. Now, if we bring a piece of matter close, let's say close to this dipole, that could be the sample or a small molecule or whatever. Now what happens is that this dipole, this point dipole in the sphere, induces a polarizability in this tiny little object. And this in turn now acts back on the dipole. And what happens? This dipole becomes stronger. That means that the dipole becomes stronger, the near field becomes stronger around the object, so the near field intensifies, but also the scattering becomes stronger. And this we describe then later on by an effective dipole moment here. So that's the mechanism actually how the near field goes into the far field. The near field interacts with the sample, it acts back, it makes the dipole, the effective dipole, stronger, and the stronger dipole then subsequently also radiates more into the near field. So that's on the basis of a single particle, and that can be very exactly modeled with the point dipoles. There are no approximation needed and nothing, so this is really pretty accurate. While for tips, you need to do a lot of simulations, and these simulations nowadays, so Isabel, one of my students, is sitting here. It still takes weeks to get a near-field spectrum calculated fully numerically if you take the whole tip into account. All right, so maybe that's a good moment to stop now. It's exactly 1 o'clock. Right.
Thank you very much, Rainer. Very exciting talk. Questions?
Thank you, Rainer, for a nice introduction. I have not a question, but more like a comment, or you can say criticism, to your, it's also on the last slide on the image about the two different, well, if you, no, you are not changing slides. Yeah, like when you say there are two, here, there are two options. So you eliminate the tip, it reflects from sample, goes back, and you eliminate sample, it reflects to the tip and goes back. I'm not sure it's the right picture. If you don't have surface waves, you focus the beam, so the beam size is, I mean, everything is much smaller than the wavelength, so it's not ray optics anymore. So there is no such reflection back and forth. It's just all together.
It's there. You can measure it, and you see it. And it's, let's say, a very simplified picture, of course. But I agree with you that there's all diffraction, and this simple drawing it's very simplified indeed. But this is indeed a far-field effect, and this far-field effect we can eliminate. And Lars will show this. And that is why this is the next thing that I will come up with. So we have the incident field, and then we have this reflection that we model with R. And I want to come to this. So in principle, it should be the incident field 1 plus R, and then we go backwards, so square. But this is too simplified picture, and that's why we put here a C, a constant, or a constant, a parameter C that is empiric. And that depends on many parameters. And we find, for example, empirically that in certain experiments this is 0.3 for whatever reason. And that accounts for actually all these diffraction effects and so on. I mean, it's a model. Huh? I mean, simply putting a point dipole above a surface is already not correct, because this is a sphere, and if you bring the sphere very close, you have higher order multipoles. And I had many fights and discussions, for example, with Mark Stockman on this when I started, because he was always saying, well, first of all, you have an antenna. Yeah, right. And then you have higher order multipoles. Yes, true. So this all is not a correct model. Of course not. But it's so intuitive, and it describes everything that I have ever seen in s-SNOM qualitatively, but not quantitatively. And the same is true for this picture. And this is not the true picture. And I will actually show later on, once you're with the topic, there's actually a second model that I see more and more again showing up in literature. That was actually the original model that was introduced. It was slightly different, and this one actually many people still using, and the thing is you shouldn't use that. For example, that one is really wrong because it violates energy conservation law. I will come back to this later on. So in short, in my opinion, it's a very powerful model because it's simple, intuitive. You can calculate it. I mean, in principle, in half a day you have implemented it by yourself. But of course, it's not accurate. I mean, nobody is claiming that. And all these bits and pieces here are okay, roughly. Huh? So don't take it too serious if I draw these errors. But it's a very excellent comment. So I appreciate that you said it.
Okay. Any other questions? Then if not, let's thank Rainer again for the great talk.